Hi everyone, welcome back to the security stream for the GSE conference. My name's Jamie Pease, I'm the chairman of the security stream. Just a few words before I hand over to our presenter today, Henrik. So this is session 2AH for the purpose of feedback. I'll again remind you at the end of this session to do that. So just keep that in mind. The QR code is down there if you want to get your QR code scanner ready. That will take you directly to the feedback for Henrik's session. The presentation will be uploaded, and I don't think it's there at the moment, is it, Henrik? But Henrik will do that at some point, so that you can actually download that from the agenda. And don't forget as well that this session is being recorded. So if you do have to drop off for whatever reason, then in a few days' time you'll be able to listen to the replay from the links that we provide. Also, don't forget our charity as well for this year. Please donate to that if you can. Be very grateful. Also, just a quick reminder, I did mention this yesterday, but we've already got the date penciled in for our next security working group meeting, which is going to be held on the 4th of February, 2021. That's not that far away, folks. And that's going to be basically hosted entirely over Zoom. So we're not actually going back to a face-to-face meeting at this moment in time. So just pencil that in your diary. An announcement will come out about that over the next few days. So without further ado, I'm going to hand over to Henrik. Now I've got to try and get this right because you did tell me Luxembourg.
Almost, yeah, it's very close.
Almost there. So you heard Lenny in his previous session on the security stream talk about the Crypto Competency Center. So Henrik actually works in the CCC, which I'm sure he'll explain, and he's actually there today. So Henrik, the stage is yours, sir. Thank you very much.
Yes, thank you, Jamie. Yes, and as mentioned, my name is Henrik Luxembourg, and I work with the IBM Crypto Competence Center in Copenhagen. So it's either 3 C's or 4 C's, as Lenny mentioned earlier. And I work as a solution architect and product owner for most of our products and solutions. What we will talk about today is not a specific offering or anything. We will talk about quantum safety, quantum safe encryption, and how we embark on the journey in order to make our cryptographic environment quantum safe. For the time when quantum computers became commercially available with a strength that actually enables them to do the bad things about our existing cryptographic algorithms. So let us move to the slides that I've prepared. This is one of IBM's favorite images in the context of quantum. This shows our quantum computer. I think this is the 20-qubit one. We are obviously moving ahead on the development path towards 50 and 70 qubits. But this picture is a few years old. I've been lucky enough to go to Poughkeepsie and actually see the computer. But when you see it live, because it's like almost close to absolute 0 degrees inside, and there's a vacuum, so you cannot really distinguish it from any other tank. It could be a water tank, it could be something from a diary. But nevertheless, it's an impressive thing, and when you know what it can do, it's even more impressive. Okay, we have in this context here with the cryptographic world, we operate with 2 days or two contexts. We operate with Q day, and that's the day when quantum computers can break or seriously weaken existing cryptographic algorithms. And then we operate with the agile crypto concept, and that's the ability to quickly change the security policies and cryptographic functions throughout the enterprise. And historically, it is a very slow thing for enterprises to go in and change cryptographic algorithms and mechanisms and functions. I think Nist 15 years ago deprecated SHA-1, but there's still places in the cryptographic environment where SHA-1 is used, such that agile crypto or crypto agility is a very important thing because we are in an ever accelerating world in terms of cryptographic operations and functions. So let's have a look on a quantum safe encryption journey. If we look at the 4 points, we have the discovered and classified data, and we have the crypto inventory. For that, we need some kind of crypto analytics tool to help us figure out what do we actually have and where are we actually today. Because time-wise, we are somewhere in between these. Most enterprises know and can classify their data in terms of health data, payment data, tax records, etc. But how are they actually encrypted, or potentially even are they encrypted, and should they be encrypted? Then we have the next notion, as I mentioned, or the next concept, which is crypto agility. And this is about to create centralized crypto functions and expose them throughout the enterprise such that you, from very few or relatively few controlled areas, can go in and control which cryptographic operations and algorithms are actually taking place within your enterprise. And finally, we have the quantum safe encryption, the QSE, as we do abbreviate it. It has had various abbreviations over time. It has also been called PQE for post-quantum encryption and others, but I kind of like QSE, and in this context here, because I find it a little bit catchy to say QSE or GSE. So I will kind of have this in all the slides, and maybe that's something for you to remember and say, okay, where do I find something about quantum safe encryption? There was QSE or GSE. At least I hope so. Let's look into the agenda or the abstracts. I will start by an introduction set of slides with setting the scenes. Then we will move into the inventory part of the crypto journey. We will then look into how to combine the insights that we have built up with the latest risk and technology outlook from quantum research. We will look into how to establish the enterprise crypto as a service, which is what we consider a prereq for the transition to agile crypto, such that you can have a policy-based approach to your risk. And finally, we will do a summary on the quantum safe embark on the journey, such that we will kind of have these 3 or 4 slides telling us what are the steps that lies ahead of us. And let's start by setting the scene. We do have Shor's algorithm and we do have Grover's algorithm out there, and these are both quantum computing algorithms. And Shor's algorithm is a quantum computing algorithm for factoring any given number in prime factors. Shor's algorithm will target asymmetric encryption, public key encryption, sign verify functions, etc. Then we have Grover's algorithm, which is a quantum algorithm for searching on unsorted database, and it may also serve as inverting a function algorithm. Grover's algorithm will target symmetric encryption and was invented by Lou Grover in 1996. These are kind of the mathematics behind the reasons for having fear about cryptographic algorithms once the quantum computers become commercially available in a scale large enough to actually operate and execute these 2 different algorithms. If we look at Shor's algorithm, then we have this 2048-bit composite integer, which is like a 2048 RSA key. If we look into the problem, that's to find the prime factors. If we look into the expected computation time, with the most powerful computers today, it cannot really be achieved. Whether we are talking tens of thousands of years or hundreds of thousands of years is not really of any interest, because any value of breaking it will be long gone by the time that these are actually done. But if we look into Shor's quantum algorithm, the computation time is expected to be down to some hours, meaning that now it is actually a situation where keys may be broken, encryption may be broken while the data is still valid. If we look at the actual work where we are right now, then we have a not so large composite integer, and the same problem is finding the prime factors. If we use the human brain as tool, then it's very easy. But actually, IBM in 2001 did manage to execute Shor's algorithm on a 7-qubit computer, and it actually worked. So even though splitting 15 into prime factors is not a huge problem, it's worth noting that it can be done, and with the increased power of quantum computers, then we will also be able to factorize much larger composite integers. Then if we take a look at Grover's algorithm, the ability of Grover's algorithm to perform the invert in function EE when y equals f of x, then given y you can find x, makes it a potential threat for symmetric encryption. There's a study carried out in 2015 on the estimated quantum resources needed to apply Grover's algorithm on AES encryption. And if we see the result of the study is depicted in this table, where you can see the size of the key to the left and the number of qubits needed to actually do a invert function. So what the conclusion is that it seems prudent to move away from 128-bit keys when expecting the availability of at least moderate-sized quantum computer. And I think we can expect at least a moderate-sized quantum computer being available, maybe not within a decade, but it will be there, meaning that our AES encryption will also be affected. In the next two slides, we will then look at the consequences as they are predicted for cryptographic algorithms. And we can see here that RSA public key encryption is expected to be broken. Ecliptic curve cryptography is expected to be broken, and AES key strength is expected to be halved in size. And that leaves us with these possibilities. So to say, AES 256 symmetric key for encryption is still considered secure. The SHA mechanisms of 256 or SHA-3 hashing functions are still considered to be secure, even with the availability of quantum computers. RSA public key no longer secure. ECDSA, ECDH, the ecliptic curve cryptography no longer secure, and DSA, the finite field cryptography for signatures and key exchange, will no longer be considered secure. So the threat is, even though it's theoretical, then it is fair to say that it is real, it will arrive. We will get to a point where some of our today well-known and secure cryptographic algorithms are no longer secure. Then let's talk a little bit about quantum encryption versus quantum safe encryption, because quantum cryptography, that's the science of exploiting quantum mechanical properties to perform cryptographic tasks, including quantum key distribution and quantum digital signatures. Quantum key distribution, that's a secure communication protocol between special hardware devices using quantum mechanisms. And I think the Chinese claims that they have had such a distribution channel running for a few seconds, exploiting quantum mechanics in this context. Then we have quantum random number generation. Random number generation is one of the very central functions in cryptography, because that's the one that actually creates our key tokens for use with the cryptographic operations. And again, the quantum random number generators, these are special hardware devices that generate random numbers from quantum effects that can be used in cryptographic operations. All these three things are not there yet. What we are dealing with in today's world and where we are trying to get is the quantum safe encryption. And that's cryptography that runs on today's computer. It requires no new special hardware. It can be brought to function with what we already have of hardware security modules or software encryption as we know today. And it's secure against current and known future attacks. And that's a very important notion, because it means that we can actually get started already now to secure our cryptographic operations and algorithms against the upcoming quantum computers. Yes, and then a few comments about what actually makes an algorithm quantum safe. Algorithms based on mathematical problems for which there's no known quantum speedup. And that is the whole thing about cryptography. It's about creating a key or cryptographic algorithm that a computer cannot break within reasonable time. So if the change or the introduction to quantum mechanics in the computer, the introduction of the qubits, really doesn't deliver any speed up in the computation time, then we consider the algorithm or the mathematics behind it to be quantum safe. It's not the same as saying that it will always be quantum safe, because new attacks may be discovered in the future, but that applies equally to the classical cryptographic algorithms and to the upcoming quantum safe algorithms that we are currently working to develop and to deploy. Yes, so let us take with this setting the scene, where we now know that some of the known cryptographic algorithms will be broken, will not provide any protection. The AES and hashing SHA mechanisms, at least the larger sizes, will still be considered secure. And there will be new and upcoming quantum safe algorithms that can be executed on today's existing hardware used for cryptographic operations. Then let's have a look at the on the next step of, or the first step of the quantum safety journey. We will look into how to create an inventory of the existing IBM C crypto environment. And for that, we'll just dwell a split second on the journey. So we are down here in the discover and classify data and crypto inventory, where we do want to utilize some kind of crypto analytics tool to tell us what do we actually have in our crypto inventory. Yes. So on a COS mainframe, we can obviously look into ICSF to see which keys we actually have available. But the utility 5.5 can, for instance, list the keys in our CKDS. But it may prove difficult to get an overview, since the search, the view, and the grouping possibilities are limited. and you may have a huge number of keys. This one here is from our test and development system where we have more than 27,000 keys. So going in and grouping them and trying to figure out which ones are actually considered to be weak, which ones violate our policies, that can be somewhat difficult. In the CCC, we do have a tool called CAT, or Crypto Analytics Tool, and it can collect security relevant information. It can analyze, give you easy to use graphic, or with an easy to use graphical client that is currently Eclipse based. It can give you highlights. It offers comprehensive data views of cryptographic security on the system. And it allows monitoring to ensure that programs, keys, and cryptographic functions are set up and protected, complying with best practices. It eases the policy and compliance. Well, enforcement is probably not the correct word. It should actually have been controlled. Sorry about that, guys. And it helps administrators to understand weaknesses and gaps, and to prioritize improvements. So looking at the graphics here, we can see that there's a cryptographic analytics tools database where the data collector picks up information from the various systems, the ICSF, the key stores, ArcF, and information about the Crypto Express cards, and some environment information also. These are all put into the database, and from the desktop application, you are then able to query the data that was gathered, and you are able to do some analysis based on what you actually see, and you are actually also able to have a policy check applied to the various groups, and you are actually also able to define the policies yourself. If we look into a data collection and how we can create an inventory for this, we have the extracted ICSF setup information from the ICSF address spaces. We have CKDS, PKDS, and TKDS information, the trusted key block data, and the tokens. And if we look at the drop down from the tool, we see ICSF configuration, we see protected verbs and utilities. We can see informations about the crypto card, key data sets, and then we can see informations about our various keys for the various cryptographic algorithms. And we have a ArcF information set where profiles, users, groups, and class options, certificates, key rings, and so forth are all collected. And if we look into a single details as an example, then we can look into our desk keys, where we can see that we have a few triple data keys. We have a lot of double length data keys for our various key types. We can also see when the key was created. We can see when it was updated, and we can see, if we want to, we can actually see information about the individual key. But for this context here, where we want to have an overview of our inventory, the overview that we have here can give us a very good and comprehensive look. We can go in and outline that we only want to see double keys, for instance, if those are the ones that we consider to be weak or against enterprise security policies. And looking into the output from a single policy execution, for example, we have a policy check performed here for the ICSF configuration, and we can see that, and since this is our test system, I'm not really concerned with the fact that we are non-compliant. Actually, it's a good thing to have non-compliant issues for demo and presentation purposes. But what we can see here is that the policy checks performed for desk keys tells us that there are multiple keys that have the same key check value. And that actually means that there's a lot of keys using the same key token, meaning that we have probably copied keys from here, there, and everywhere, from one place and into a lot of different places without actually worrying about important things like key usage, where are the keys, what can it be used for, etc. Then we have possible weak keys identified. We can see that there's a lot of there are keys that are non-compliant to the warning key length policy, and that is in this case here I know it's set up to not allow or to give us a warning in case we have double disk keys in the system. And as we saw from the previous screen here, we have a lot of those actually, and those will then be a typical target for our next step, where we want to go in and centralize our cryptographic operations. But let's move to the next slide here, which is a little bit about how we do combine the insight with the latest risk and technology outlook from quantum research. And actually also this point from the abstracts, we were a bit optimistic when we said the latest risk and technology. I would actually have liked it just to be the current, because pretending that we know the latest from quantum research is probably not true. So with what we know today, we have kind of these risk baselines. The cryptographic algorithms use the protocols in which the algorithms are embedded, the size of the keys, and how they're distributed and stored. The context, we have the evaluation of fault-tolerant quantum computers, the number of physical qubits required for each logical, and the connectivity of the qubits. We have the application context of our crypto consuming applications. We have the security time value of the data that is being collected or stored. We have the difficulty in upgrading the application infrastructure. And on the risk context, the improvement of the quantum cryptanalysis, the development of new quantum algorithms potentially. These could pose as new threats, as we mentioned earlier. And then the development of hybrid cloud and quantum solutions, and the strength and evolution of the, and here we have the post-quantum cryptography algorithms actually still used. And if we just look at the graphics, 2019, 2020 is where we are. We're doing our risk analysis. We have Q-Day lurking somewhere out in the future. We don't really know when implementation deadline will be. Our current expectation to Q-Day, as mentioned earlier, is that we are most likely a decade from Q-Day, but nevertheless, as we have also learned, or as we also do know, it can take a long time to upgrade cryptographic algorithms throughout an enterprise, because they are potentially embedded deep down into application code. If we look at the Nist timeline, where we actually are today, then we can see that in July 2020, Nist called for the round 3, which is considered the final round. Back in 2017, the draft call for proposals. There was a formal call. There was obviously a deadline for submission, in which a lot of cryptographic or quantum safe algorithms were submitted. Then there was an evaluation during 2018, and in early 2019, we entered into round 2. And then there has been a further detailing of the algorithms, the quantum safe algorithms, and now we have reached round 3 by July 2020. And I'm glad to say that IBM is is still in the running with the crystals, dilithium crystal kyber, the lattice-based cryptographic quantum safe cryptographic algorithms. Maybe just for information, the Chinese standardization competition actually ended New Year's evening 2019. So the Chinese have actually already selected their quantum safe encryption algorithms for their standard. And it's also good to see that all three winners are lattice-based, like the ones that we in IBM is also betting at the Kyber and the lithium keys. And if we have a detailed look at the Nist, the third and final round that came out here in July, then we can see that Nist selected 15 of the second round candidates to move into the third round of the standardization process. And of the 15 advancing candidates, 7 has been selected as finalists and 8 are selected as alternate candidates. The finalist for third round, we still have the crystals Kyber and the crystals dilithium in the running, as supposed by IBM, which is of course very reassuring for us that we can generate these keys and prove that they are actually quantum safe. So if looking back on the timeline, it potentially be 2023 before we actually do have a final saying from Nist, because that's the current stretch of the draft standards phase. But eventually we will come out, and we still have the possibility, or we already now have the possibility to operate with these things. But then how do we then establish an enterprise crypto as a service for our enterprise, such that we are able to move towards the agile cryptographic or the agile enterprise cryptographic operations? The enterprise cryptographic environment may spread over several different systems with individual HSMs, application landscapes, etc. And in order to create an enterprise crypto as a service, there are some considerations to make. The crypto as a service must be reachable from throughout the enterprise. It must have enough capacity to meet the enterprise demand for crypto operations, also during peak hours. And our expectation, or our knowledge within IBM, is that IBM-C can deliver such a crypto as a service because it has the strength, it has the reliability, and it has the scalability to serve an enterprise. That is one of the cornerstones in the IBM-C world. That is that we hardly ever have any breakdowns, we hardly ever have any failures, and we can deliver huge amount of cryptographic power also. So if we look into the choices to make, sorry, I was a little one slide too far. How to establish the enterprise crypto as a service. And again, if you establish an advanced crypto service provider client-server environment in your enterprise, then you will be able to centralize the execution of crypto operation and hence establish the crypto as a service throughout the enterprise. And at the same time, you can actually achieve a better utilization of crypto hardware, a simplified enforcement of the crypto policies, and an easier administration of crypto hardware. It is such that utilization of crypto hardware throughout the world is, when it really runs high, it's in the area of 10%. The KEX crypto adapters on an COS mainframe have a lot of spare capacity that you can actually expose to your enterprise and use in a lot of other situations. So if you look at the graphics to the left, then we have all the various application environments. We do have REST consuming applications. You may have cryptographic applications running on AIX in Linux, on Windows, on IBM I, and there will be cryptographic usage in the cloud where you potentially do not want your cryptographic keys in the cloud but want to have them on-prem. Then with the ACSP client exposed, deployed in all these environments, and an ACSP server running on your COS mainframe, then you are actually able to expose the cryptographic capabilities of the Crypto Express adapters running on an IBM C mainframe. Simply by connecting over the network using a TLS connection, and you will have user checking and security checking via RAGF from the ACSP server. So we are into the well-known, well-established and secure model of C mainframes in terms of resource access control and the like. So in order to establish an enterprise crypto as a service and also to make it eligible for a future quantum safe encryption, which choices should I then make? And as we saw in an earlier or in two earlier slides, the symmetric key encryption using AES 256 will still be secured in the post-quantum era, and likewise with the hashing using SHA-256 or SHA-3, they are also considered to be secure. These are already available to the crypto environment. These are well known and can be established or implemented right away, at least without doubt about the crypto strength, etc. But you potentially may have a lot of application updates to perform. Then for sign verify option or the public key algorithms, these we expect will be broken. But we already have the possibility to know, so we should look into the key algorithms from the Nist final quantum safe third round and use those as the recommended choices, meaning that, for instance, Crystals Kyber or Crystals Dilithium will be well served in this area. Yes, and we already do have some support in the area of Crystals Dilithium, for instance. From Lenny's session earlier, we heard about the EKMF tool that has an EKMF web or an EKMF workstation option. The EKMF workstation already now supports generating dilithium keys based on the CCA version 7 or the latest version of EP11. Well, actually, the EKMF workstation uses CCA, so the CCA 7 already now has support for crystal dilithium keys. And we can see from within our key template editor depicted in the graphics on the left, key template is where we express our key policies, such that a key generated based on a key template will always have the same attributes and metadata. We can see in here that we can choose a dilithium algorithm in the asymmetric key generation. We can also see that we can choose the key size. The key size is currently set to a 6x5 key size. It's a matrix-like operation, and already now the standards are beginning to operate with stronger key sizes, 7x6, and it is expected that by the when we reach the end of the standard, or the standard is decided, we will probably need to operate on 8x7 keys. They do grow in size, and the key tokens themselves are actually larger than, quite a bit larger than the conventional key tokens as we know them today. But this is all things which are being incorporated into the support for the dilithium keys. So as mentioned, we are already able to generate these keys with the EKMF workstation. And if we look into our advanced crypto service provider, then we are actually already also able to operate with them. We do have extended our test suite such that it will generate a set of crystal dilithium keys, and it will, as you can see from the slide here, it will generate a signature, and it will verify the signature afterwards. We can also see the average transaction time for the signature is actually rather much higher than the average transaction time for the verify, because in the context of the signature, we are also generating the key inside the test suite. These are not keys that are stored. These are just keys that are generated and used on the fly for the purpose of testing the algorithm and the operations. When I mentioned earlier that we can generate the keys from the workstation, we can operate them via the advanced cryptographic service provider or crypto service provider. Then currently with dilithium keys, these are clear keys. They're not stored in CKDS key stores, etc., meaning that we can keep them in database instances, but they're not as such operational via ICSF as it is currently. But this just proves to show you that you can already now start working with crystal dilithium keys in your development and sandbox environment to see what does it actually require for me to move into or to implement these algorithms to stay quantum safe. Finally, we have the open quantum safe area where you can go in and already now also download a open quantum library set that can run on Linux, where there's also support for dilithium and Kyber, meaning you can, for instance, test TLS connections using quantum safe encryptions already now. And this could also be a good starting point for you to go in and explore what will this actually mean for me and my enterprise. And then how do we then, when we have established our crypto as a service environment, how do we transition to agile crypto with a quality-based approach to the risks? And for that purpose, I do have a single slide that again takes its offspring in the advanced cryptographic service provider and a concept that we call user-defined function. A UDF, it's custom code which implements business-specific functions. It runs in ACSP server. The ACSP server exposes the UDF supporting the defined cryptographic policies. It extends standard CCA ICSF APIs. It can support a varying number of parameters and parameter types. It can make permission checking through RAGF. It is ideal for implementing crypto as a service function because with your user-defined cryptographic or your UDF crypto running in the ACSP server, you can externalize your crypto policy such that it may be updated dynamically, and you can, from the ACSP client side that may run in all the environments that we saw earlier, even in the cloud, you can do a user-defined function call, and you will have RAGF-based checking to the resource. and then you will have your cryptographic operation executed on the COS mainframe based on your crypto policy, and the reply returned to the ACSP client with a user-defined function call, and your keys or cryptographic elements will never have to leave your mainframe. And this could be a very neat way to introduce the quantum safe cryptography transparent to the application, because what it means is that you will, in your cryptographic backend with your crypto as a service component, you will update your user-defined functions to support the quantum safe cryptography, and it will be completely transparent to the application. The application will still do as it did always. Please sign this transaction for me. Please encrypt this data for me, etc. So there will be, once we are in the agile crypto environment, there will be no major need for updating of application code in order to introduce new cryptographic elements. Yes, so having said all this, we think we are at the time where we should move into the summarize of our journey. So our journey will today start with building our inventory for the entire enterprise crypto environment. We need to take all cryptographic operations into account. Then we need to identify policy violations and weak spots. And we will build, or we will update our enterprise crypto policy with choices that were made to achieve the quantum safe encryption. And this is where we say that the choices that we have today for the symmetric cryptographic operations, that's the AES 256, which is a very good candidate, and the hashing algorithms 256 and SHA-3. These are considered safe, as we've already seen. For the asymmetric, the public key cryptographic algorithms, which we consider to be broken once the quantum computer has reached a sufficient size, sufficient number of qubits, then we already now have the quantum safe algorithms ready to use for experimental operations, such that you can say, this is what I want to do. And if you truly build an agile crypto environment where you will be able to have your cryptographic operations, your cryptographic policies expressed centralized and in a manner such that they may be updated more or less dynamically, then you are a very, very close step towards the end of the journey. So basically, once you're there, your cryptographic journey has ended. You have done your crypto analytics, you have centralized your crypto functions, you made sure that they are exposed through the enterprise and they are policy driven, and eventually you have a crypto policy that says how to implement the quantum safe encryption algorithm for your cryptographic operations. So, well, maybe not by tomorrow, but this is a way to get there. And as Lenny mentioned earlier today, and I don't know, I should actually have said that, plan and document as you go through all these steps, such that you always know where am I heading and where did I come from. Why was this a sound decision when I made it? Is it in the agile world, we all know that decisions that were sound yesterday may be not so sound today, and the agility means that we can actually fairly easy go back and change them. So with that, I will end my QSE, GSE, and see if there are any questions. So I will turn it over to you, Jamie, for a short while.
Thank you, Henrik. It's excellent. Thank you so much. And that, I've got to say, that quantum machine, I want one. They look so good, don't they?
Yeah, they actually do. We have tried to get Poughkeepsie to attach one of them to the network, so that you can go in and see that my COS machine has 4 CPUs and 1 queue, but
Oh, God.
it's not there yet.
No. So does anybody have any questions? If you want to, I can unmute your line. So if you either want to post something in the chat or just say, Jamie, please unmute my line. I'd like to ask a question. Please go ahead. And just while we're waiting for people to, if anyone wants to put any questions in the chat, Henrik, your session, you've already posted the foils for your session, haven't you? I say foils, your slides for your session. You've uploaded that already, haven't you, to the GSE website?
Yes.
So what you need to do is, if you can't see a little blue man, and I think somebody has said that they don't see any of the presentations uploaded for the security stream, there are actually everybody except for the first session yesterday has actually uploaded their decks. So if you can't see the little blue man on the any of the presentations, just press F5 just to refresh your browser on the agenda, and then hopefully you should be able to see them. And you click on the blue man, and providing you're logged into my GSE, you should be able to download. So we've got a question actually, Henrik, from Darren Smith. Hi again, Darren. He says, when will Kyber be available?
Kyber is in the design phase, and I expect it to be with the upcoming releases of EP11 and potentially CCA 7.3. We have not had our usual crypto councils this year due to the pandemic, where where Klaus Werner from IBM in Böblingen or Richard Keesley from IBM US usually updates the charts with the upcoming releases. So I'm not quite sure actually, but they are in the in the welding actually.
Thanks, Henrik. So, I mean, we were just rolling out HTR 77D1 and Crypto Express 7, but will we need the next release of FMID and possibly the next release of coprocessor, or do you think it will be able to run on those?
No, it will be able to run on those. I think currently the support with ICSF and the key stores are the one that kind of prevents us from going full operational with these quantum safe keys, because as I mentioned, we can already generate them on the fly and operate on them, but the only place we have where we install them is actually in the database instances, so they're not really out there in the operational cryptographic environments.
Okay, thanks so much.
Yep.
Any more questions? We still have 5 minutes to go till the top of the hour. Nope. Okay, we'll keep an eye out anyway. Just sort of closing. So thank you so much, Henrik, for taking us through that. A virtual round of applause. And thank you for bringing up the session feedback. Jamie's going to go off on one again about that. So it's like I say, it's really important that you give feedback for all of the sessions that you hear on the GSE conference. I mean, the first is, of course, the feedback for the presenter. It's for their benefit as well to understand, what you liked, what you don't like, and to rate the session as well as conference feedback. Don't forget, so that we can understand where we can make things better for your conference next year. Also, if you are required to maintain CPEs or CPD credits, your certificate gets generated through my GSE based on the sessions that you have actually given feedback for. So, you know, that's, you know, if you want to get your full credits for every single session that you've attended, there's another incentive to actually to give the feedback for your final certificate. Also, yeah, thanks Henrik for bringing up the charity slide. Please don't forget to donate if you know whatever you can for our GSE charity this year. You can either use the URL to go to the Virgin Money Giving website or use the QR code. Just use your QR scan and it will take you directly there. And also a quick reminder that, like I said, we're planning to do our next GSC Security Working Group meeting on the 4th of February 2021. So pencil that in your diary. And also we're on the lookout for presenters as well. So if you are interested in presenting for that session, it'll be a full day event and be hosted over Zoom. You know, please send me an email. Look out on the GSE Enterprise Security website. You'll see my contact details there. But thank you. If there's no more questions, like I say, thanks once again, Henrik, for taking us through that. Well, I'm sure we'll have you back at some point to sort of find out how things have moved along. It was great having you. And one final point, we have a 30-minute break now. It's almost 1 o'clock, so we've got a 30-minute break. Up next on the security stream is Mark Nelson, and he's going to come and talk to us about RACF and the parallel sysplex. So that's at 1:30. So please do join us if you can for that. You'll be most welcome. But enjoy your lunch break or your whatever time of day or breakfast wherever you are, and we'll see you in 30 minutes. Thank you.